Alright guys, in this video we're going to look at what we can do with some of those values we're getting in our stoichiometry problems. So we're going to look at limiting reactants and theoretical yield. Now, there's a couple of different things I hope you picked up in the other video and in the reading this week that are really important definition-wise. The first is that reactions can only proceed as long as there are reactants available to react, right? It's kind of like your car. Your car only drives as long as you have gas. Gas is the limiting reactant to the car, to the engine. When you look at a reaction, the first reaction that's going to run out, the first reactant that's going to run out or be consumed all the way, we call that the limiting reactant. And it's really important to identify that reactant. As far as real life, we want to make sure the limiting reactant is the most expensive reactant in the equation, because we want to make sure that we're spending our money well. If you have a rare reactant or something like that, that may also be something you want to make sure is the limiting reactant in your reaction setup. All of the other reactants that are left over, they're called excess reactants or reagents. Excess reagents, the word reagent, reactant can be used interchangeably. Now, when you find the limiting reactant, you can actually find the theoretical yield at the same time. The theoretical yield is the maximum amount of product that you can make based on the limiting reactant. When you find them, all right, you can start to draw some conclusions about your reaction. You can start to describe your reaction as a whole. You can even find the excess mass, that is the amount of reactants that are left over. So we're going to do all of those things in this video. Now, when you're watching this, all of the next 3 slides are just practice problems. That's all that's going on here. If you want the concepts, go look at the overall video or the reading. This is the actual calculations themselves. I want you to pause the video on each slide, and I want you to try to solve them, okay? Once you've tried to solve them, or if you think you've solved it, or if you hit a snag, then play the rest of the video and watch my explanation. Obviously, because we're doing stoichiometry, you need a periodic table, a calculator, and some scratch paper. So let's jump into the first one. The problem says a solid white phosphorus, which is P4, reacts with oxygen to produce tetraphosphorus dicoxide. Determine the limiting reactant and the amount of product formed if 25 grams of each reactant reacts. How much of the excess reactant remains once the reaction is complete? So we're actually looking for a couple things here. Remember, pause it, then come back and watch and see if you got it right. So the first thing we need to do is we need to write an equation. They don't give us one. So we know we have P4. We know we are reacting with molecular oxygen, because anytime oxygen by itself, it's O2, plus they tell us O2. And that's going to produce tetraphosphorus, so P4, dec oxide. Dec is the prefix that means 10. I need to balance this equation. Obviously, it's not balanced. I have 2 oxygens on the left and 10 on the right, but that is an easy balance. 1, 5, 1 are my coefficients. Now that I have a balanced equation, I can get into my givens. So I'm given 2 things. I have 25 grams of each reactant, and they will ask me, they say, how much product is formed when they react. So I only have 1 product, so that's good. We need to convert each of these reactants to that specific product and see what we make. So this is a 3-bracket question. I know that because I'm starting with grams, and I'm looking for amount, which is, you can read amount as the word mass. So I'm going grams to grams. So grams to grams, which we know is 3-bracket. We know it's going to go up bracket. We know it's going to go periodic table, molar ratio, periodic table. So we can set that up. So 25.0 grams of P4. Grams of P4 is going to go to 1 mole of P4. So that's just 4 phosphorus added together, 4 times the molar mass of phosphorus from the periodic table, which we'll get to in a second. I'm going to use my balance coefficients. 1 mole of P4 results in 1 mole of P4O10. And then we need to get mass, so 1 mole of P4O10, and this is going to be some grams of P4O10. P4O10. There we go. All right, so there's my setup. These two gram numbers come from the periodic table. So phosphorus times 4 is 123.9 grams. 4 phosphoruses and 10 oxygens is 283.9 grams. So let's run our first question here. So 25 divided by 123.9 times 283.9 gives me 57.28. 57.28 grams of P4O10. All right. So here's what we're looking at in this piece of math. If I have 25 grams of P4 and all the oxygen I could ever want, I can make 57.28 grams. But that's not what the question asks us. It asks us what we can make if both react. So we need to run our other one. We have 50.0 grams of O2. We're going to set our brackets up the same way. So O2 is 31.998 grams of O2, right? 2 times 15.999 moles of O2. We see on our balanced equation that 5 moles of O2 produces 1 mole of P4O10. And then my last bracket is just the molar mass of P4O10 again. P4O10, 283.9 grams. P4O10. All right, we run our number. 50 divided by 31.998 times 283, divided by 5 times 283.9. That gives me 88.724 grams of P4O10. Okay, so now we have two numbers, and we have to figure out which one of these two numbers, and I'm going to switch over to red for a second. All right. So I have two numbers. So I have this number here, and I have this number here. And I need to figure out which one of these two is the theoretical yield. And here's the thing about the theoretical yield. It is the lowest amount of product that you can make given two reactants, because one of the two is going to run out. And this is the one that is the theoretical yield. It's smaller than 88, so this is the theoretical yield. The theoretical yield is made by the limiting reactant, which in this case is 25 grams of P4. So we would write P4 limits, and we could set up limits, not limity, limits, and the theoretical yield is 57.28 grams of P4O10. All right. So we have determined the limiting reactant, P4. We've determined the amount of product formed. Good, we got the theoretical yield. So we've done two things. Now we need to do the last part, the one that says how much excess reagent is remaining. So this is actually a pretty easy conversion. I do the amount of product that I made, 57.28. So I take the theoretical yield of P4O10, and I'm just going to convert it back into oxygen, because oxygen here, O2, is in excess, right? Remember, anything that's not the limiting reactant must be in excess. So I'm just going to convert it back and see how much oxygen I used up to make the theoretical yield. So 283.9 grams of P4O10 in 1 mole. All right, pen, come on. P4O10. There we go. don't know why this is looking like chicken scratch. Must have something on my pad there. All right, anyway, 1 mole of P4O10 produces 5 moles, or is produced from 5 moles of O2, and 1 mole of O2 is 31.998 grams of O2. All right, so this bracket, this stoich setup, is going to tell me how much oxygen I used to make exactly 57.28 grams of my product. So 57.28 divided by 283.9 times 5 times 31.998 is 32.27, we'll say 28. 32, oh my goodness, 32, there we go, 0.28 grams of oxygen used. All right, that's what it cost me. That's not what the question asks. It says how much remains. So now I just do a little subtraction. I started with 50 grams. I used up 32.28 grams. And so 50 minus 32.28 is 17.72. 17.72 grams of O2 remain. What in the world, pen? There we go. In the worst handwriting ever. All right. A little box. Put that in. Something to keep in mind with stoich problems. If you have multiple questions in the question, right? A question asks for multiple answers. Not a bad idea to check them off as you go. So what have we gathered here? What's our outcome? Well, if you react 25 grams of phosphorus with 25 grams of molecular oxygen, you're going to make 57.28 grams of P4O10, and you're going to have 17.72 grams of oxygen left over. There we go. That's what we know. All right. Number 2, practice number 2. Again, pause it. All right. Try to solve it, then come back. Coffee is delicious. Okay. Let's go over here, grab the blue pen. So this one says, nickel-ion batteries operate by the following reaction. Hey, they gave us a reaction this time. Good for us. How many grams of iron 2 hydroxide are produced by the reaction of 5 moles of iron and 8 moles of nickel? Let's see, what would that be? That'd be a hydroxide of nickel, NiOOH. We haven't really talked about how to name that. When we're looking at this, all right, well, I'm looking for grams, but I'm starting with moles. So if it's moles to grams, moles to grams, all right, I know that this is not going to be 3 brackets. This is only going to be 2 brackets. And I know that it's going to go mole ratio to periodic table. It's just going to take two brackets. So here we go. We have 5 moles of iron, 5.00 moles of iron. There we go. And where are we at? We have 1 mole of iron in the reaction, 1 mole of Fe, and we're trying to get to iron 2 hydroxide. So this is our iron 2 hydroxide. This is the product that we care about. And we can see that it's a 1-to-1 ratio. So 1 mole of FeOH2. And we need to know mass. So 1 mole of FeOH2. And we looked that up on the periodic table. Add 1 iron, 2 oxygens, and 2 hydrogens, and we get 89.859 grams of FeOH2. There we go. So I only need 2 brackets in this problem because I'm just going moles to grams. there's my first one. We're going to go ahead and set up the other one. So 8.00 moles of our nickel compound. OH. All right. Now, hopefully, you can already tell just by looking at the mole ratio which one is going to limit. And we'll talk about that more in just a second. But hopefully, you're seeing what's going to happen here. But let's write it out anyway. Our second one is the same bracket as above, right? We want to compare apples to apples. So we need like terms. All right. So there we go. So in the first one, I have 5 times 89.859. That's all we have going on. So we could make 449.295 grams of our product. At the bottom, we have 8 divided by 2, so 4 times 89.859. And it should be pretty obvious that this one's going to make less because 4 times 89 is less than 5 times 89, right? So 359.436 grams of FeOH2. All right, so again, the limiting reactant limits how much product you can make. So when you're comparing the two, the one that's lower must be the theoretical yield. It must be made by our limiting reactant. So we'll switch over to red and we'll box in our answers. NiOOH is my limiting reactant. Thus, that number, 359,436, is my theoretical yield. Now, in this question, that's all I'm looking for, right? It says, how many grams of iron can I make? So really, the only thing I need here is the theoretical yield. This would be my answer. But when we do it this way, we find everything all at once, right? We find who is in excess. There we go. We find who's the limiting reactant, and we find the theoretical yield all at once. Now, this is why this is important. We're going to look at, not in this video, but in another video, percent yield. And I'm just going to give you a snapshot of what's coming. Percent yield is the actual yield divided by the theoretical yield, AY over TY, times 100. It's a pretty simple concept. But if you find the theoretical yield in part A of a problem, and then part B says, what's the percent yield? Well, you've already found theoretical yield. You've saved yourself some steps. So because we're going to look at percent yield later on, that's why I like to find limiting reactants and excess reactants this way, okay? Last one. So lithium reacts spontaneously with bromine to form lithium bromide. If 25 grams of each reactant are present during determine the limiting reactant, the mass of lithium bromide produced, the excess reactant, and the excess mass. So here we're going to put a lot of stuff together. The first thing you probably notice is that there is no balanced equation. So you need to figure that out. So again, pause it, try to solve this whole problem, and then come back. All right. So we have to write ourselves a balanced equation. So I have lithium plus bromine produces lithium bromide. So this is a synthesis reaction. And lithium bromide, we would do our cross-charge method to get. So lithium's +1, bromine's -1. So it's just going to be LiBr. Easy reaction to balance, right? All ones. So there we are. Li plus Br yields LiBr, lithium bromide. Now, I've got 25 grams of each, and we want to know who's limiting. Now, I'm going to work both of these out, but bromine is way bigger than lithium. So if I have the same amount of each in mass, well, that means I have way fewer moles of bromine because bromine weighs more, which tells me bromine's going to limit. So logically speaking, I should be able to do this much quicker, right? I don't need to write all this out. But I'm going to write it all out just so we can see how it works. So we have 25 grams of lithium, and this would be a 3-bracket conversion because we're going grams to grams. So grams of lithium per mole. So there's my periodic table bracket, my molar mass bracket. We know it's a 1-to-1 ratio of lithium to lithium bromide. All right. And then LIBR, 1 mole of LIBR, all right, is 86.845. 86.845 grams, LIBR. Now, we can look at that and say, okay, that's going to be a decent number, right? 25 divided by 7 times, so 25 divided by 7 is like roughly 4-ish, 3 or 4-ish. 4 times 86 is going to be a number that's decently large. Now let's look at bromine. 25 grams of bromine. So bromine's a heavy halogen. It weighs 79.904 grams. 25 divided by 80 is a fraction. So while the number up here is going to be larger than 86, this number is going to be smaller than 86. But again, hopefully you can work that out on your own. 1 mole of Br produces 1 mole of LIBR. So there's our molar ratio bracket. And 1 mole of LIBR, we've already figured out how much it weighs, 86.845 grams of LIBR. All right, so let's run our numbers. 25 divided by 6.941 times 86.845 is 312.797 grams of LIBR. 25 divided by 79.904 times 86.845 is going to give us 27.17 grams of LIBR. All right, as usual, we're after the smaller of the two numbers, so we can say bromine is my limiting reactant, and my theoretical yield, right there, 27.17 grams of lithium bromide. So I found the limiting reactant, all right, I found the mass produced, that's the theoretical yield. I found the excess reagent, right, because we found them at the same time. Lithium is in excess. Yeah, there we go. All right. So now all I need is the excess mass. So I have one more conversion to do, and then a little bit of subtraction. So I take my theoretical yield, 27.17 grams of LIBR. I'm going to convert it into my excess reagent. So I'm just going to do my bracket in reverse. 86.845 grams of LIBR in a mole of LIBR. My molar ratio is still 1-to-1 because that's what my balanced equation tells me. All right, top to bottom cancel out. And then 1 mole of lithium is 6.941 grams of lithium. So let's see how much lithium we consume. So 27.17 divided by 86.845 times 6.941 gives us 2.17 grams. So 2.17 grams of lithium were used up. Right? 941. We're used up, but it says how much is the excess mass, what remains. So we started with 25, so we do 25 minus 2.17. 2.17. There we go. 25 minus 2.17 tells me 22.83. 22.83 grams of lithium remain. There we go. So flip over to red. We'll box in our answers. And we have found the excess mass. So there we go. All four things. 3 conversions to do that and a subtraction problem. All right. So that's all the practice problems I'm going to work for this. These are the kinds of problems that you're going to see with limiting reactant and theoretical yield. We will see an application of theoretical yield in percent yield, which I talked about a minute ago, but that'll be in another video. If you have questions, let me know. All right, I'll be glad to give you a hand.